We went through all these variations there. Okay. I'm going to go ahead and, as I said, get started simply because this thing on. Yeah. That way I can. All right. The last thing we went through all the gates our last meeting up there, and just kind of a quick review of them up there. I'll just go through them quickly. Right there. And then when I say quickly, I do mean very quickly. Just to kind of review. Try to turn that off. Right there. All right. Just kind of a quick review. Right there. This is better attendance than I had in my microprocessor class, which that particular class, I hate to say it, they're on the short semester. They can't afford to miss a day. You know, when you do this in 7 weeks, I'm used to doing these courses in 16 weeks. So, but I actually have more hours in a week typically. The U.S. system that I'm used to is 2 1-hour lectures, then a 2-hour lab that's there. So here they've got scheduled like 2 hours and 2 hours. It's about the same, but it's 14 weeks. But then you've got the final week, a review week there. But it seems a little shorter here because 2 hours is too long for a lecture. It's about right for a lab. But this class here, because they don't give me a lab room, we can't do real labs. So I really just have lectures up there and demonstrations with the software. And I will be bringing a development board down to show that there. So most of the labs will be just, the only labs will be demonstrations. We have no lab rooms up there. You know, it's a little different than my normal what I'm used to. Normally for a digital course, I'm used to, yeah, here we're sneaking in. We're gonna start putting a toll gate in. Everyone that's late gets charged 1 ringgit per minute. Per minute. So right now that's 11 ringgit each. That's there. It's called my advanced retirement fund. Right there. Okay, getting back to where we're at. We went through the gate, and I'm not going to go through all these again, but I just want to review what they are. We've got the OR gate. The output is true if any of the inputs are true. Right there. So A or B or C, you use the plus sign. Right there. Again, the AND operation, the other major gate that we're looking at, the output is true if all the inputs are true. Now this says if A and B, and we treat this as multiplication, the way that we write that. And the reason we do that, you'll see later on in today's class when we start going through some of the Boolean rules, right there. So that's there. Operations, you know, this is a 2-input AND gate, that's a 3-input AND gate. I've seen AND gates with as many as 16 inputs, right there. So they can be quite large. That's it. So those are the 2 symbols. I could have just stopped right there for those. Those are the majority of what we're looking at. Then the next one is the inverter, the NOT gate. And you'll hear the term, the complement. If you're writing software in assembly, normally the command that does the NOT function is a complement command. So in other words, CPL space A means complement A. So whatever A is, every bit is then reversed to a, you know, if it's a 1, it's now a 0. If it's a 0, it's now a 1. That's there. So normally it's called, they say it's a NOT gate. 90% of the people I know talk to refer to it as an inverter when you talk about the gate. It's called an inverter. That's there. The symbol for it is that there, and unfortunately the recording doesn't record where I'm showing the pointer, but that's all right. I'm not going to sit there and try to use the mouse behind that there. That's there. But sometimes you've got, if you're using a word processor, most people will use this A apostrophe at the end. If you're dealing with text citing, or if you use the equation editor, so when I write the final exam, I may use the equation editor, then I can put the bar across. You know, the equation editor gives you that flexibility. Most word processors don't. It's just we live in a word processor world for most things. The A apostrophe is used right there. So if you're going to be doing multiple, that's there, you know, go through that. That's the symbol for it. The bubble always denotes inversion. We'll see that bubble a lot right there. Right there. So skip that there. Skip that there. We've talked about that there. These are the basic rules, summarized rules for and or not, right there. We talked a little bit about writing the equations, you know, right here, coming up with what the equations are. Remember that I said that there would be a question, at least part of a question on the final exam where you will have to do that, where you'll be given a circuit and you have to come up with the equation. And you'll also be given the opposite, where you're given an equation and you have to draw the circuit right there. So you know to do that. Take note that you always do the and operation first. The other day when I was trying to do an example, I forgot that rule and I started to go down the wrong path, and I got about, as soon as I looked at it, I realized I did the wrong thing. Oh, the star is downloaded first. Okay, so I can read the newspaper later on. That's it. So the parentheses works the same in Boolean algebra as it does in regular algebra. That means you do that operation first. So if you look, as you look at this first one, you have the and operation on the left-hand side because you do that first, then you or it with the C. Here I put the parentheses on the bottom, so the or operation is done first. That's there. So that reverses the order in which we do things right there. This is the parentheses. So those parentheses make a big difference. That's there. So you have to keep that in mind. And remember that these equations, okay, now we're cooking 15 rings per person. That's there. See, 15, we're at 30 plus 22. Oh, 50. I'm making a good pay for the day. I could tell UETL to keep my salary and just collect the late fees for students that come to class late. That's there. Okay, that's there. But these parentheses do make a difference. And remember that this is going into hardware. These are actual physical gates that we're putting in there. So these equations, you know, go one-to-one from hardware. That's there. And the end gate is a circuit. That's there. It's got a TTL circuit. We're not going to get into what those circuits look like in this class. There are some courses where you actually look at the silicon and see what it looks like. That's there. Actually, we're going to find in this class we're not even going to look at the gates because we're going to do everything in programmable logic when I do the demonstration. That's there. So, all right, whenever there's an inverter, this shows the inverter here. Sometimes what they'll do is they'll not put the triangle, but they'll put the little dot right here at the input. They'll put the little circle there at the input. Right there, and leave the triangle there, and they'll just move this bubble right up to the tail end of this right here. And the same thing here, they show the inverter here. Normally they would show the little bubble there, and that is actually a NOR gate. Now, if you don't have a NOR gate available to you, and you have to use an inverter, then you would draw it this way. It depends on what hardware you're actually going to put it into. But if you put a bubble on here, usually, now if you're doing an actual circuit design, it's going to go on to, you know, TTL logic chips, and you're drawing this into a CAD program such as OrCAD. You know, and OrCAD is a program, and you don't have to remember what OrCAD is. If you have, there's multiple ones. It's the one I'm most familiar with. In OrCAD, you would actually put the inverter there, and you would assign pin numbers to it because the inverter chip is a 7408 chip, and again, you'll see some of these numbers later on. That's there. I think the OR gate is 7402 in the right there, and I may be wrong, but that's there. But an inverter is typically a 14-pin chip, and it has 6 inverters on it. So you would put down which inverter you're going to use off the chip, because that tells the person who's going to lay out the printed circuit board how to wire that. That's it. So if you're designing these circuits, you would assign a pin. This would be like U1, U2, and this would be also U2 and U1. That's there, because typically you'll find 4 OR gates on a chip, or 6 inverters right there, and you'll find 4 OR gates up there, because there's 3 inputs, 3-pin devices. You need 1 for ground up there. So that gives you 3 times 4, that's 12 pins, plus the other 2 for VCC and ground right there. The inverters, you've got 2 pins, and that leaves you how many left? 7, right? So leaves you 12 left, so that means you can have 6 inverters. That's there. And we'll look at these actual chips later on. And we have the physical textbook. I think she's got the physical textbook. Usually in the back cover of most of these books, you'll see all the pin layouts of it. That's there. That's there. It's not important we look at the actual pins, but when you draw these, that's most of the time you would assign a part for those there. Okay, again, remember that we talked about, I went through this example last time, and I went through this one here. And remember that I said you have to do the reverse. You may get this equation, and you have to go back and reverse that right there. They won't be any more difficult to do these examples. I mean, I'm not going to give you something, this is a 4-input circuit. It's a fairly involved circuit. This is about as complex as I would expect a freshman class to derive. That's it. All right, now we're going to go into all the various rules. This is the order in which we should be working these things here. Let's go through them right here. Best way, analyze, allows you to double check your work right there. So when you're done, you have to use a truth table right there. That's the best way to analyze it. But okay, this is where I want to get back to. Rules for evaluating voltage. Do all inversions first of single terms. Perform all operations with parentheses, all ands. Unless parentheses indicate otherwise, which is kind of repeat from the previous one. That's there. Now we're up to 21 ringgit per person. I was telling the class earlier I'm going to start charging 1 ringgit per minute late charge. That's there. That's there. So now I'm not going to charge any fee. But okay, but this is the order in which you normally would go through this. And practice makes perfect. That there. After the Hari Raya break, expect to see a homework assignment where I'll give you that there. And what we're going to be doing here is we're going to be looking at how to simplify expressions. In regular algebra, you want to simplify your expression. So we have a series of rules we're going to go through, and these are all the theorems of Boolean algebra we're going to talk about. That's here. So this is for evaluating to see whether the output is true or false. Right there. The way I showed doing it there is to create a truth table. I put 1, 1, 0, 0, 0, 0, 0. This is 5 inputs, and then just see what the output is. And I did the example step by step. Very tedious process. For this problem, this would be extremely tedious because that's 5 inputs. That means I have to go through that process 32 times. I showed you last time a little software package, not a little software package, it's a very large software package. It's 2 gigabytes to download. That's there. That will go through and analyze a circuit. And it gives you the truth table. It doesn't give you a truth table, but it gives you the timing diagram. That's actually a simpler way of doing it, but you still need to know how to do it by hand. The most you'll see on a test, if I ask you to come up with a truth table, would be 4 inputs. So again, put that down as part of your test question. So I've already given you 3 or 4 test questions right there. Now, one test question is you're going to have to be able to come up with an expression from a circuit. The next one you need to come up with a circuit from the expression. The third one is you need to come up with a truth table from a circuit right there, or an expression right there. So So right there's 3 test questions right off the bat, right there. So I'm kind of highlighting those as we go along. Okay, this is kind of how you go through the process of doing the truth table. That's there. So you do all the inversions first. I usually just start to the left and just move on through. That's the way I usually do it, right there. This is doing it that's from the circuit. This is doing it from the expression. So that's a little bit different process, right there. So if you're going to evaluate it using the expression, then you've got to do it this way. If you're doing it from the circuit, then you do it my way. You put 0, 0, 0, and you just kind of go through there, and then you erase it and do the next step right there. So best way to circuit is to use the truth table. That's there. The truth table is important. And the reason the truth table is important is because you can have 2 circuits that look exactly, or I worded it wrong, that look completely different. They look completely different. But at the end of going through the truth table, they perform exactly the same function. They're equivalent circuits right there. So we're going to be going through some Boolean algebra techniques. We're going to look at Boolean algebra and solving these things using the rules of Boolean algebra. Then we're going to look at Cartograph maps. And we're going to take very complex expressions, put them into a truth table, and then we're going to go through and use some techniques to simplify them right there. So, and the reason we simplify these is that gates cost money and they use power and they take up room on a PC board. So if we have an expression that takes up 8 gates, and we can shorten it or make it smaller and fit it into 4 gates, then we've cut the circuit size in half. Right there. Now there are some things that it may create some problems, and we'll look at some of those later on, right there. So it allows you to analyze 1 gate or logic combination at a time. Double check your work right there. We went through this example right there. This is the example I went through last time, where we created this U here. We created V and this W right there. And we did this truth. We went through here. It's a little hard to read, but we said U is equal to A naught. We looked at A and we inverted that. B is equal to A dot B, so then we calculated that there. So we took this here, A naught, we looked at these 2. And the only place that's true is these 2 right here, right there. We evaluated this expression right there. Then we did the next one, and we said B, C. We took B and C, and we and that. And then our last one, we ORed these last 2 together, right there. So that's how we generated this truth table. So what we have is this expression right here. This circuit gave us the expression for that circuit. Looks like it's A naught B right there, ORed with BC right there. This is right there. So again, a different expression. This is much more complex, obviously, as you can see. And I'm not going to go through this step by step. Later on in the semester, you may look at this and go, boy, this is a lot of work. Because we're going to find that a lot of times these steps are all completely unnecessary, but in real life. But it's part of understanding what's going on when we get into the more advanced techniques right there. So as we look at this here, this is our 4 inputs right here. And I think I will move over here and try, in this case, use the mouse. Oh. Well, all right. As we look at this right here, this here is just A, B, C, D, and that's 0 through F written in binary form right there. That's all that is. And then I generated all my various columns here. Now they skipped the A naught column here. On the previous example, they had a column in there for A naught right there. They skipped that one there. So, and they evaluated, they set T is equal to this top one right here. This is A naught BC right there. And then the next one is U. This is U right here. And then we've got B is set here, and then this is our final output right there. So again, a very tedious process, but it's one that with practice, it's fairly easy to do. I can do this. It's done exactly the same way as I did the last one. I put these slides up. Has everyone been able to download these slides? Up there. I suggest that you go through this one here. It's actually going to go through. No, they're going to. Matter of fact, they don't do the example that's there. So, okay. All right, getting back to right here. I was looking to see whether they up there, but this is a problem that could be used. There's no solution given to you for it, so I suggest that you probably work through this as basic practice on how you would come up with this truth table. This is the final results here. Now, I want you to notice something with this final result right here. That it's only true in one location. Everyone see that? So I could tell you right off the bat that I could reduce that to one gate. Well, two gates. Because I can tell you right now that expression is A naught B C D will give me the exact same truth table. So that's the case where I look at this truth table and I can say that all I could do is take this circuit here, A naught, right there, A naught, and have a 4-input AND gate right there, and I'm done. I would get the exact same truth table. And if we went through and did the analysis of this later on, we'll see this whole thing will reduce down to A naught B C D right there. So, and that's why we're going to go through that step there. So, as you can see, we're looking at an example which I know reduces greatly. That's there. All these gates half these gates are unnecessary. Right there. Okay, implementing circuits, that's there. Again, we've talked about that there. Right there. So this is right here. So this is what we call, we're coming up with what's called a sum of products. Right there. These are our three product terms, AC, BC, BC naught, A naught, BC, and then when we OR the output together. This is called a sum of products. Right there. Right there. This happens to be shown as a product of sums. Right there. And I know we went through this last time. Again, I'm spending half an hour reviewing, but this is important information. Sometimes, and it doesn't bother me to go through material twice. Right there. Okay. The last two gates we talked about were the NOR and the NAND gates, and all that basically means is that we put a bubble on the tip of each of those in order to invert the output, right there. And that's where we ended last time, right there. And this is showing here that we've got an OR gate, two inputs there, and a 3-input NAND gate, or NOR gate. Got to remember NOR and NAND. You guys pronounce that net in the front of it. Sometimes I'll forget that. So, okay, now we're going to get into what today's lecture is talking about, and that's Boolean theorems. There's a series of these. We're going to go through them one by one. We probably won't have time to do too many examples of them, and I don't want to kind of cloud them with a lot of examples on how to solve equations, because I know that I won't see any of you for 2 weeks after today, right? Nobody will be here next week, right? So that's there. And we don't meet till Thursday. We don't meet this Thursday, right? So yeah, because I didn't realize Thursday's classes were canceled anyway this week. So, this is my first time around this park, going through this calendar, and the person next to me told me I should look at the little book there, and they tell when the holidays are, because normally this up there. So I mean the holidays are different, but because the class schedules are different. That's there. So, and besides this timetable for your class is completely not anywhere. So we're making those rules up as we go along. It's not even in the system right there. So actually, I think they're scheduled. This class is not. They put this class to start the 27th of July. So the last 3 or 4 weeks we shouldn't have even been meeting if you look at the timetable in the system. Okay, only laws that we're going to go through these one at a time. There's about 12 of them. That's there. And the first one is that if I take anything and I end it with a 0, the result is 0. Right there. So X1 ended with 0 is 0. 0 ended with 0 is 0. An AND gate is, the output is true only if all inputs are 1, right? So if I add a 0 into my AND gate anywhere, I know the output is 0, and I can just throw the AND gate away. Right there. So it must be 0, and it's fairly obvious right there. If we compare it to normal multiplication right there. Now the next one is if we AND anything with a 1, the result is itself. So as we look at the AND gate, all we're saying here is that X ANDed with 0 is equal to 0. X ANDed with 1 is equal to X. Right there. So those are our first 2 rules. And I have to sit down and write this here, and this is where, see if I can move. Am I in your way there? You guys can still see the screen? Let me find my pen here. Uh-oh. Now here's the hard part, finding my little plastic cover for my... And if I don't pick it up now, I'll forget at the end of the class. Look for it. Oh, there it is. I've lost more of those plastic covers. They're hard to come by. It's just a display book. So rule 1 is this one here. This is rule 1, which is anything ANDing. Now we can extend this to multiples. If I have 3 inputs and one of them I know is a 0, the whole thing can go away. The output of that is 0. Now this one here, if I have 3 of these, 4 of these, and one's a 1, I just ignore that. Now later on, we'll find that we'll use this technique to use a 4-input AND gate in replace of a 3-input AND gate. We just tie the unused input to VCC right there. So it's also used for other purposes right there. So as we go through and look at that right there. So those are rules 1 and 2 right there. Now rule 3, and this, I didn't realize this was going to do this, so we got to erase all this right there, is, okay, prove theorem 3, one states any variable. Theorem 3 simply says if I AND something with itself, I get itself back right there. And that's easy to prove because X, and I'm going to use X and X in my truth table right there. And I'm going to call it Y out. This is 0, 1. This is 0, 1, right? So this is going to be 0 and 1 right there. It's the same as X right there. So in other words, if I have X ANDed with X, the result is X right there. It's all that this does right there. And this is one that will pop up from time to time. This one's an interesting one, is that if I AND X with X naught, I end up with 0. Again, that goes back to, it looks like the best thing for me to do is to toggle back and forth between one node. Right there. So if I've got an AND gate and an inverter here, and I put in X or Y, I'm going to put in Y. That way I can use X for the output. To me, it's confusing to use X for the input and output. Right there. In X, well, if Y, if I do the truth table, Y naught, Y is 0, Y naught is 1, Y is 1, Y naught is 0, right? So X, if I AND the two of these together, has to be 0 and 0. Right there. That's all that says right there. Right there. So as we go through. So there's our first four. They're fairly easy right there. These basic ones get fairly easy. The last one we're going to talk about is an interesting one right there. So then we'll do a couple of examples right there. Then if I OR anything with 0, the 0 can be ignored right there. And again, it's, X plus 0 is equal to X right there. Right there. If I OR anything with a 1, the result is a 1. And it goes back to the definition of an OR gate. If any input is a 1, the output is a 1. So if we have anything that's got a 1 as an input that they're on into an OR gate, we can completely ignore all the other inputs when we know the output is true. Right there. So it just, that's there. And we'll use these theorems later on to simplify our expression right there. Then the X one is we OR anything with itself, it's itself. That's the same as if we, with the AND gate, right there. 0 plus 0 is equal to 0. 1 plus 1 is equal to 1. Remember, that one looks confusing if you're dealing with regular algebra, right? But when we're dealing with Boolean algebra, 1 plus 1 is equal to 1. That's there. So it is confusing. And the last one for our OR gate is X plus X naught is equal to 1. And the reason that is that if we X naught, if X is 0, then X naught is 1. If X is 1, one of those two is always a 1. So if there's a 1 to an OR gate, the output has to be a 1. So if we take X plus X naught, the result is always got to be a 1. Right there. Always a 1. Right there. So I don't know if this works or not. Yep, okay. If I hit Alt F4, I can go back and forth between the two of these keys. Okay, that's there. Now we get into the more difficult ones. Those ones are the very basic rules. You need to put these to you basically need to memorize these, and that's why I'm going to go through them today, and then we're going to review them again after the holiday, since you had 2 weeks to, eat a lot, visit family, drive across the country. Some of you are taking buses across the country, I'm sure. Is anybody taking the train south or north? When's everybody leaving? Today or tomorrow? When do you leave? What? Tonight? Tonight. So are you driving bus, train? Bus, train, driving, bus. Okay. I've taken the bus all over Malaysia in the past. I haven't done the bus lately, but the buses aren't too bad. But where do these guys get their driver's license? These bus drivers. They are some of the fastest drivers that's there. So right there. So it's crazy. My favorite way to travel is usually the train, but I haven't been on a train in about 5, 6 years. You know, they were getting pretty ragged the last time. You know, hopefully they've cleaned them up and repaired some seats back there. So, all right. Now we're getting back to middle school algebra. And some of these rules are exactly the same as you had, you know, what do you got? Primary school and secondary school is what you call it here. That's there. So you probably saw these rules somewhere right around standard 5 is probably where you saw some of these, maybe form 1, something like that. But, you know, the first rule is x plus y is the same as y plus x. We can reverse the order. Now, when we look at Gates, right there. Oh, I didn't want to do that. Right there. Oh, now I got to go back and find where we were at. All right. When we look at Gates, for this right here, all this says is that this was an OR gate. And the same thing is true with an AND gate. If I hook up X, or we'll use A and B, that's the same as we hook up B and A right there. You know, sometimes it makes sense if we look at the physical, the way we connect these things up right there. So all this says is that it doesn't matter which input we tie X, A, B, or C right there. Same thing here. AB is the same as BA right there. It doesn't make any difference there. So, right there. So those are the two commutative laws right there. Now, one of the reasons they're using X and Y is because sometimes we'll expand this to more than one variable as we go through some of these examples. Associative laws are the same. Now, these associative laws do have a huge bearing when we look at hardware. And what this does is it doesn't matter whether I associate these two or these two together, or I don't associate anything at all. Right there. Same thing here. Now, when we look at Gates, whenever I say Gates, I'm thinking Bill Gates right there. What that is saying is that if we look at an OR gate, we've got A, B. Let's look at the case where this is supposed to be an OR gate. OR gate here. A, C. This is A or B or C, right? So we don't have any 3-input AND OR gates in our box of parts. But we're doing our hardware design, and I just don't have any 3-input AND gates or OR gates. Either one, it doesn't matter. But I've got lots of 2 inputs. So I could do this. A, B, C, right there. That's the same, that gives me the same expression. Or I could do this. A, B, C. So what I'm doing is I'm using two input OR gates to replace the fact that I don't have any 3-input OR gates right there. So, and it doesn't matter. All 3 of these, if you went through and did the truth table, will give you exactly the same thing. You know, the reason is it's quite obvious. The first one, if any of these inputs are a 1, the output's a 1, right? If A or B is a 1, the output of this one's going to be a 1. That's there, which means the output of this is going to be a 1. If C is 1, then it doesn't matter what A or B is, the output's a 1. And I can reverse that. So essentially, we gave us the flexibility of using 2 input gates to replace a 3 input gate right there. And the same thing is true, and I'm not going to go through them all, for A, B, C right there. And I can put A, B, C right there, and right there. So we've got that flexibility where we can easily move from right there. So those are our associative laws right there. So distributive laws are a little bit different. Now this one works the same as regular algebra right there. But what this does is it allows me to expand an expression right there. Up there. Now this one is quite sometimes used in a situation where timing glitches are a problem. And let me kind of go through, I'll do that with an example here, right there. But let me just show what this does in terms of circuits right there. And I'll do the top one first, and I won't go through it with the bottom one, but the bottom one is actually, the same type of thing right there. Right there, but, okay. What this says is that I've got the expression A, B plus C, for example, right there. And that's equal to AB plus AC right there. Circuit-wise, this is going to look like this. B, C, and then we AND that with A, right? And that's X right there. Circuit-wise, this is going to look like this. AB, AC, right there. Right there. That's what it's going to look like. Now, we would do this for multiple reasons. One reason is we don't have any OR gates. Right there. Excuse me, this is an OR gate right there. I just made a big mistake right there. Right there. There's actually only one reason we would do this. And the reason we would do this is that, as I mentioned last time I went through the Altera software, there's a timing delay. This goes here. The output changes roughly 10 nanoseconds later using the hardware that we're using. This one doesn't change right there. So therefore, this input here hits that gate 10 nanoseconds before this input change hits it. So we have a 10 nanosecond glitch on our output. Right there. It's a glitch. In some circuits, that's a problem. Some circuits, it's not a problem. Right there. So here, this one's got a 10 nanosecond delay. This has got a 10 nanosecond delay. These two signals hit here at the exact same time. Therefore, there's no glitch on the output. So we remove this erroneous signal that's going to show up at about 10 nanoseconds. And that's using the Altera hardware. That's based on using that particular type of gate right there. That glitch, the glitch changes when the hardware changes. A 74, XX family is faster than a 74 XX family. Different families we'll see later on are faster and slower than others. So this here, let's say this one here is supposed to go, the output is supposed to go from here to here, right there. That's up there. This one might, that's an easy one there. Let's say the output is supposed to stay low. Let's look at that's the case here. This one here, it's going to do the same thing right here. But if the output is supposed to stay low right here, this one might have where it goes high, or this one stays low. And this is about 10 nanoseconds because we got that little bit of an error signal right there. Because A arrives at this AND gate before the A, B, or C. right there. That's one reason we would use that right there. You know, you would think that we reduced the gate count by 1, but we've also introduced a glitch to our system, right there. We've introduced a period where we may have a wrong output, right there. So that's why it's somewhat important that you try to do that in some cases. Some cases it doesn't matter, right there. You know, but I've worked in systems that work great, no problems. A chip goes bad in the system, the technician replaces it, the system doesn't work anymore. And the reason it doesn't work anymore is because he was an old system, he used an older chip, the glitch was small enough, it did not show up on the output, did not cause a problem. You replaced a chip with one that's much faster because the older chip wasn't available. Now all of a sudden, this glitch is a problem. So later on, we'll look at other options on that there, but right there. So the distributive law, right now we're only going to use it for simplifying equations, but there are times that we'll use it. Just remove that there. Okay, multivariate ones here, up there. This one here is kind of an interesting one here, and we'll go through these one by one right here. This one here is x plus x, y equals x. And the reason that we can do that is, you almost have to use the truth table, but what you could do is you can look at this here, and you can do factoring, and that's what this one does here. X plus x is equal to x, 1 plus y. 1 plus y is 1, right there. So the y disappears, right there. The next one is x plus x naught y is equal to xy. That one's a little bit more tricky, right there. And then x plus xy is equal to x naught plus y. These are tricky, right there, and they come into play. And the first one's easy to show. The second one, you almost have to go through the truth table. But again, what you're looking at here is that if I did the same thing right there, let me remember it right here. It's x plus x naught y, right? Right there. So if you look at that right there, and you did the factoring of that right there, and there's no easy way of showing it that way there, but what you look at, that's equal to y, and how do we know that right there? So if we take y plus 1 right there, and I'm not going to go that way, just use the truth table, is the easiest way of doing it. That there, x, y, right there, and I'm going to call our output z right there, 0, 1, 0, 0, 0, 1, 1, 0, 1, 1, x, y, right here, x, whenever x is true, the output is going to be true, so that's going to be, that's going to be 1, 1 right there. That is not going to be equal to y. That doesn't make sense. Let me go back and look at that again. Something's not right. The truth table, x plus y, excuse me. That's there. That's where it doesn't make sense. Right there, it's x plus y. Let's just start over again here. X plus x naught y is equal to x plus y is what that is right there. And that actually comes out easier to see because the truth table for that x, y, and z right there right off the bat, I can put 1, 1 here, right? There. And then the other one is this one right here, and that's when x is 0, y is 1, this is a 1, and this is a 0 right there. So you can see that fairly straight from the truth table right there. Again, trying to come up with it algebraically is just not going to work real easy. by doing any kind of factoring. You just put in the truth table and you'll see that it falls out right there. Oh. Right there. And then the other one is actually going to be just simply the reverse of that there. And again, if we put that in, it's x plus x. X, is that x plus x dot y? Is that what I had there before? Yep, x naught plus xy, okay. And before I go, remember I can't do I have to push the button. The way that I go between this, well, this is wrong. This is x naught plus xy right there. And the truth table for that is xy z 0, 0, 0, 1, 1, 0, 1, 1. As we look at that right here, any place x is a 0, this is a 1, and then x1 right here, right there. So, yeah, that's supposed to be the same as x naught plus y right there. And we'd have to go through and write that truth table and compare the two of them up there. I'm not going to up there. The last one today, and then we'll go through some examples up there, right there. This De Morgan's theorem. De Morgan's theorem is a very powerful one, and we'll use this a lot, right there. This one is basically the same. There's two parts of De Morgan's theorem, and that says that x ORed with y is the same thing as x naught, or excuse me, x NORed with y is the same thing as x naught ANDed with y, right there. From a gate, that means that if this is going through an OR gate, right there, that's the same as this going through an AND gate with two bubbles right here, right there. Right there. Those two are equivalent. And you'll find some people that will draw an OR gate this way. Right there. And kind of an interesting thing is that if you look at it that way, if I put a bubble here, that's the same, and I keep pushing that there. If I put another bubble here, excuse me, I did that wrong. I put the bubble there, and I put another bubble, that says that, and I'm going to have to erase this, that an OR gate right here is the same as an AND gate with bubbles on all the inputs, right there. And every now and then you'll see somebody do that, right there. So, but that's part one. The other part looks exactly the same. This one's easy to remember, difficult to go through and algebraically come out with it. It's easier to use the truth table, right there. And there's the other part up there. And again, you'll notice this comment is each of these De Morgan's theorems can be proven by checking all possible combinations. In other words, you set up a truth table for that in order to prove that's true. There's no way using algebra to prove this because the rules of algebra don't apply, right? 1 plus 1 is equal to 1. So we know that normal algebra does not apply right there. So that's all the rules that we're going to look at for solving simplifying equations. But then this is where things get interesting in this class up there. And up there is we're going to look at expressions and we're going to try to simplify them right there. So let's go back here. Right here. Now let's go back to that one that we had here. And right here that I said it could easily be simplified. Now let's see whether or not we can simplify it using those rules. This one right here. Right here. So Copy. Okay, so our expression is A naught B C A or D naught, right? And we'll go back and look at what that's going to simplify to. The first thing I'm probably going to do is probably expand out the first one right here, which is use De Morgan's theorem to make this the same as, and again, you can use De Morgan's theorem on parts of an equation. So A plus D is equal to A naught D naught right there. Right there. So when we do that, we're left with A naught B C A naught D naught, right? Right there. Is that correct? Well, A naught and with A naught is equal to A naught, right? So we're left with A naught B C D naught. This simplifies down to 1 right there. Right there. So that's the way that we would apply these rules here. Going back to our right there from present slide. Remember I said that I looked here and I saw 1, 1 right there on the output. And I go across here and it's A naught B C D naught right there. By inspection I could see that from looking at the truth table. But by using Boolean algebra, I reduced it down to that expression. So now I'm left with a single 4-input AND gate with 2 inverters right there. Now, it's that simple in terms of hardware. We don't know it because we don't know what gates we have on our board right there. I'm hoping that they have more examples here. If not, I didn't bring examples with me. If not, we go to the textbook and pull some examples out. Right there. And I'll be real honest, this one here, I quite often forget to use this one. That's there. Okay, equivalent circuits. All right, they're going through those equivalent circuits that I talked about briefly a few minutes ago from De Morgan's theorem right there. In other words, this here is a NOR gate, and that's the same thing as an AND gate with the 2 inputs inverted right there. The alternate symbol for a NOR gate is right there. And I mentioned that a few minutes ago. And this is the same thing with the NAND gate right there. Now, they're jumping into something that I didn't realize. I'm just going to go ahead and follow the slides and go with the lead. We get into something called the universality of NAND and NOR gates. And I'm going to go back one note and do this without using the slides. And the slides may cover the same thing better, but I have my method. Let's make the assumption, and this is a very valid assumption that we can make, but I can take any function A, B, C here, and the output X right here, 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 2, 3, 4, 5, 6, 7, 8. All right, that's our truth table. And I could put any combination of ones and zeros on the output right there. I just made those up at random. I don't know what they are. I probably shouldn't have put as many ones here, but that's all right. There'll be a large circuit, but what you're going to see is that there. So what my function is every place here's a 1. Right here, draw. Right here, here's a 1. Oh. Right here, every place there's a 1, I can write that expression right there and OR them together. I'm going to create a sum of products from this truth table expression for this by inspection right there. So the first one is A not B not C, or A not B C not, or A B not C, or A B C not, right? Now, just for clarity, I'm just going to circle this one, and that goes to this one here. This one goes to this one. This one goes to this one, and this last one goes down here to this one, right? So we've got 3 AND gates, and I'm going to show them as just 3 AND gates with bubbles on the input there. Just so you know, I'm not going to draw this up there. So I could draw this circuit right there by, again, I'm going to, let's go back to black right here. Right there, the first one, I'm just going to put 4 AND gates right here. 4 AND gates, and I'm going to put A, B, C going to all 4 of these, and I'm just going to draw a bubble here, 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 and a bubble here, right there. So this is A, B, C, A, B, C, A, B, C, A, B, C. There's an alternate way of drawing this, which is quicker with CAD. And this all goes into an OR gate, right? Right there. Right there. So we have, again, this is any 3 input circuit I can do this way. Any. Right there. I just randomly picked it. All I did is look at the ones on the right-hand column here, and for every one, I just wrote down a product term for that. And if it's a 0, I put a not over it. So it can be done, by inspection. Just simply you draw that there. So now, if I put a bubble on here and here, what have I done? I've taken an inverter and run it through an inverter right there. That does not change the logic. There's no change. If this is a 0, this is a 1, this is back to a 0. If this is a 1, this is a 0, this is back to a 1. I have not changed that. So what I've done there, and I do this for all these right here. Right there. These are all now NAND gates, right? Right there. This is also a NAND gate, going back to what we just showed a few minutes ago. But I've got these inverters here, right? I've got all these inverters, right? Well, that's no problem. I take a NAND gate, and I tie the 2 inputs together, and I've got an inverter. So I can take any 3 input function and do it with just using NAND gates. I don't need any other type of gate. That's the only type of gate I need. I can do everything I want with just NAND gates. Now that's a very important theorem, or concept, and the reason it's very important is because there's an entire generation or a classification of digital logic called masked gate arrays. They're called gate arrays. And what a gate array is a sea of gates. It's a bunch of gates, 2 million, 3 million, 4 million NAND gates placed on a single piece of silicon. And then you can develop any circuit you want by just connecting them up however you want. So when they manufacture the silicon, and silicon's manufactured in layers. Here's a big piece of silicon right there. And what they do is they put a mask on it right there. They expose it to a gas. Then they put another mask on it, expose it to another gas. And they can take all these wafers and generate these gates, and then the topmost layer is the interconnect. And they don't do that one. That one's reserved until the customer wants to order a gate array, and they give them the configuration, and then they do that last layer out there. And it allows you to do huge, very inexpensive custom ICs, digital ICs, without having to go through the expense of creating all the masks. You only have to create one mask out there. And there's companies that do lots of gate arrays out there. And then there's also devices out there called field programmable gate arrays that we'll look at some of those later on, that you can actually do those in the lab right there, that's there. So you have this versatility of gates. Now let's take this one step further, and let's look at this expression right there. And this expression, if someone help me out, A naught, B naught. Actually, you know what I can do? Lastly, I don't know. Copy it. Oh, I just broke the software. How long have I been talking? Not quite an hour, that there. Okay. Well, that didn't work too well. So we will just simply redraw that, rewrite that. So, all right, A naught, B naught, A naught, B naught, C plus, I believe it was A naught, B, C naught plus A, B naught, A, B naught, C plus A, B, C naught, right? Now, I'm going to do something quite drastic here, and I'm going to invert the entire thing right there. And this is going to be called, this is equal to X. So X naught is equal to A naught BC plus A naught B C naught plus A B naught C plus A B C naught, all with a line across that right there. So I just inverted that. Now I apply De Morgan theorem right there. So X naught is equal to A, B naught C, all inverted right there, times A naught B C inverted, A B naught C inverted, A B C naught inverted. Now I apply De Morgan's theorem again, right there. So as we do this process, x naught is equal to A plus B plus C naught, right there. Now that's an important step. You see how I got that there. That's it. Because I applied De Morgan's theorem to that there. This one here is A plus B plus C right there. I invert each term as I do that there. A naught plus B plus C naught times, and I'm going to put it here, A naught plus B naught plus C right there. That's what the function is not right there. So that's what the function is not. So, and that's perfectly fine right there. Now we go back to our truth table right there. In our original truth table, looks like this here. I'm going to shrink this to where I can write it over here. Actually, right there. I'm just going to shrink it down. Can you see what that's still readable though, right? So this time I'm going to read the zeros out. If I read the zeros out, I'm reading out what x naught is. That's there. So instead of reading the ones, I'm going to read the zeros. Right there. And as I read the zeros, I'm going to end up right there, and that something doesn't look right. That's there. Yeah. Because that gives me what x naught is right there. So if I read the zeros, I get x naught. And then I'm going to invert the entire thing at the endpoint right there. And actually, you know what? To be honest with you, I think I don't want to finish this example. I think it's going to confuse. This example is getting nasty enough that just before the break, what I've covered is important enough. I don't want to leave you with this right there. Right there. Let's just stop, ignore everything I did here, right there. We'll come back to that after the break, okay? We'll leave it at this one right here. And the reason I want to leave it at this one here is because going through both these is a lot to absorb in one sitting. And my philosophy is that if I give you too much in one class, you're not going to remember half of it. So I'd rather stop with what you can remember right there. Besides, everyone wants to get ready to pack, right? This is your last class for the day, right? So after here, you're going back to the hospital, packing your bags, and get ready to go home. So you're ready to go, you're ready to leave. So, okay. With that said, I am going to stop this recording. Right there. I talked for an hour and 15 minutes, so that's actually, out of 2 hours, that's actually pretty good for me. I'm not